Okay, here we are. Welcome everybody to Edge AI Talks. I'm Pete Bernard, CEO of the Edge AI Foundation, and we have a new co-host this morning. Dimitri, welcome.
Hello there, I'm Dmitry Maslov, and I'm a senior embedded systems engineer at Edge Impulse, a Qualcomm company. Besides that, I also have a YouTube channel about Edge AI and wrote a couple of books on the topic as well.
Awesome.
So a bit qualified for that.
Yeah, you're good. You're good. And yes, Edge Impulse is a Qualcomm company. What company isn't a Qualcomm company these days? I mean, really, you know. It's,
well, there are a couple of them. Yeah,
still a few left that aren't Qualcomm companies. But no, great to have you here. I think just before we got started, you mentioned you were in Dubai for the big Edge Impulse offsite. Are you out of Dubai now? Or where are you at?
Yeah, I'm back to Amsterdam. Amsterdam is where my home base is.
Awesome.
With significant amount of suntan. So that's from Dubai.
I'm here near Seattle, so you can tell no suntan.
Very white. Very white.
So we're gonna bring on Reza Rahimi from YASP. We're gonna talk about compilers today. So compilers are sort of like I call them the kind of the godfather of all tools in the software space. Maybe people don't realize how important they are, but they're critical. And in the AI space, you know, compiling models and optimizing them is kind of the name of the game, especially in the edge space. So we're going to talk about that today, get some live demos. Before we get into it, let me do some PSAs, some public service announcements. One of them is we have our, first of all, see everybody at Embedded World. So I know Dimitri's going to be there.
Yep.
And we're going to have some YASP people there, but we're going to be there with a booth, and we're going to do some live streaming. We're going to be sponsoring an event with IoT Stars and doing a whole bunch of fun things. So hopefully we can see everyone at Embedded World. If you want to meet with us, go to our website, email me, contact me on LinkedIn. We'll get together. So that's one PSA. The other is we have our event in San Diego a couple of weeks after that. So every year we get together in the US for a few days, kind of an Edge AI Palooza event. We have talks and demos and panels and workshops. I think about 15 hours of workshops. We have evening mixers. We're actually going to have a keynote from retired Rear Admiral from the US Navy. We're going to have a panel on defense tech. We're going to have a evening reception on the deck of the USS Midway. So it's going to be pretty amazing. So if you have a chance to go, you can go to that URL down below, San Diego 2026.edgeaifoundation.org, and save your seat. So we have subsidized pricing because we are a nonprofit. So it's dramatically less expensive than the usual commercial conferences. And then with special pricing for academics and academia. We actually have a professor from UCSD and another from UC Riverside giving keynotes. We have Durga Malati, speaking of Qualcomm. You're one of your execs.
Yeah, that's great.
The EVP there is going to be giving a keynote. Intel, DeepX, the CEO of DeepX will be there. So anyway, crazy fun in San Diego, March 24th to the 26th. So that's my other PSA. Okay, so that's the end of the advertising. Now we go on to our regularly programmed entertainment here. Let me bring on Reza.
Hello.
All right. Welcome, Reza. Welcome.
Welcome.
Thank you. Hi, Pete and Dimitri. Thank you for having me. And I'm saying hello to everyone watching online. And thank you for listening to me today.
Awesome. Yes. I was going to say to remind folks, this is a live stream. So if you're watching on YouTube or LinkedIn, feel free. Part of the deal here is you get to ask experts questions as they talk about things. And so feel free to throw that into the comments, and then we will throw them up on the screen in a curated way so that we don't completely interrupt Reza all the time. But yeah, ask your questions here, and also let us know where you're watching from, because we get an incredible worldwide audience with these things. It's amazing. I'm always trying to figure out the time zones when people are saying where they're coming in from. So please go to your chat window and send in some stuff. Let's see. Here's this person. Eswar Varden, student exploring Edge AI and currently focusing on how lightweight models come around and resource. Well, you are in the right place, my friend. Okay. You are here. We are all here now. Good. Okay.
Continuing
so Reza, go ahead.
What you're saying about the Edge AI, we're going to have our compiler. So I'm going to demo the compiler today, but we're going to have it showing how our model is going to run on a low power chip in Edge AI San Diego. So hope to see you guys all there. Yeah.
Yes, Reza will be in San Diego, so you can meet him in person and see some live code. Yeah, one of the cool things about our conferences is we have this expo where people kind of show their tech. So it's not really a sales conference. It's like it's people show their tech, and then you can see how, ask them how it's working and stuff like that. So a very hands-on thing. So yeah, you should definitely come to San Diego. Someone is calling in from Lincolnshire, UK. Awesome. Nice horse. That's your horse. That's cool. And then, here's someone from Canada. So, Reza, you're in Canada, right now?
Yes, correct. I'm joining from Halifax, Nova Scotia, and our company, we have an office in Montreal. Yeah.
Awesome. Yes. And we're saying Montreal's a pretty cool city, and you have tons of snow there. Yeah, which is all good. Speaking of the weather. So excellent. Oh, and here's someone coming in from India.
Nice.
All right. Good for you. And then one more before we get started. Scotland. Adrian from Scotland. Nice. Good. Okay, so let's get into it. So why don't we bring up your we're going to do a few slides, and like I said, people can throw their questions in the comments, and we'll gather them. I think Dimitri and I will kind of step back and give you the floor for a little while, so you can get into it, and take it from there.
Sure. Yeah.
Sound good? All right.
Awesome. Thank you. So what you see in the title is Compiler 4.0 Agentic ML Compiler for the Edge. What do I mean by 4.0? Because we never discussed 1 or 2 or 3. So let me take you back. Let's go back in time and look at when we created one of the first compilers and one of the first languages that a human can read. Let's say if the language was assembly, the compiler was assembler, and the job was to take the code, translate it into bytecode or binary, and run it in the target hardware. So that was the beginning, I would say, the beginning of the revolution of the compilers, because that was not the first compiler for sure. But internally at YASP, call that type of compilers compiler 1.0. And if you look at the evolution of the languages and compilers from that point, if you particularly pay attention to C and C++ and look at GCC or Clang, what they do is they reading your code, optimize your code, and then turn it into low-level code for the target hardware that you're deploying to. So two trends are important here. They're optimizing the code, and they're generating low-level code. So they're generating assembly code, and they eventually going to use assembler to turn it into bytecode. So the compilers that kind of came after this first wave, they're not going directly to bytecode. They're kind of turning into low-level code, because writing, let's say, a huge database with assembly is difficult. But now writing it with C and C++ is relatively easier. And if you look into, let's say, maybe, don't quote me on this, but let's say 40, 50 years ago, all the companies, gaming or the companies building software, they were looking for assembly engineers. But after that, we saw right now, even right now, how many companies that you know that are actually actively looking for assembly engineers? Of course, some hardware companies for building their own driver, they need assembly engineers. But even gaming companies have moved on, and they're only writing in C and C++. Moving on from that, the ML explosion and now the LLM explosion, now we're talking about models. But how would we use this compiler for models? We saw a lot of compilers evolve from this. So we go from the 2.0 to kind of 3.0. And what I call the 3.0 compilers are the ones that compile models into binaries that can run on our target devices, such as TorchCompile or MLIR or TVM. And what do they have in common? It's very interesting. It's similar to 2.0. That they read your graph and try to optimize your graph at IR level. By IR, I mean intermediate representation, that you know what is the operation, what are the input outputs, what are the data types, and they try to optimize it at the intermediate representation level. And then you get the optimized IR and then turn it into low-level code. So the same scenario happens again, optimization, code generation. But the issue here is, what's the pain is here, that in CPU search space, the search space is kind of limited. We can create a lot of, let's say when you do a plus in your C++, creating an add function that adds 2 integers or 2 tensors is easy for a CPU, writing it for CPU and finding what's the best kernel to replace your add function. But in ML, what is it? There are many target hardware. So some companies are using NPUs, some companies are using TPUs, some companies are using GPUs, which like has a SIMD, single structure, multiple data kind of algorithm set for parallelization behind. So these kind of like the search space are going to be huge, and the data types are FP8, FP16, and you have a machine that has FP8 cores, and you have another machine that has a FP16 core, so you have to have kernels for all of them. And even talking to the vendors themselves, like the hardware manufacturers, it is a pain for them to create kernels for all of these architectures that they build. So there must be a better way. And we want to do the same thing in the compiler architecture. We want to do optimization and then code generation, but we want to have an agentic system writing the code for us. So we can write code for your target hardware and your model. Awesome. Let's continue. And so the way we want to compile the code is you have your data set, you create your model through one of the training frameworks like PyTorch, Cross, TensorFlow, and then you use yasp.compile, our product of a compiler, to turn it into a binary that can run on your target hardware. It could be NVIDIA Jetson Orin, it could be AMD Ryzen AI, or it could be like as big as, let's even like the server grade GPUs like the H100s and B100s. So how we do that? So let's say PyTorch and Yasp, like it's easy as a standalone pip package that you install the package. And then we have a graph tracer. The graph tracer, what it does, it tries to read your graph and turn it into an intermediate representation. We want to know what is the graph that you want to optimize. And then we send that to our backend. At backend, we do two things, optimization and code generation. As you remember, the trend of compilers. In the optimizer, we want to optimize the model. We call it at like IR level, and also decompose it into separate pieces. We call it partitioning. So we partition the model. Let's say your model is combined of 3 different backbones. We combined it into 3 different models. Or your model has breakpoints like if the data was like this, go right way, and if the data was like that, go left way. We turned it into 3 different models, and we treat it like that. And then on the code generator side, that piece goes to the model, and we try to go down to the math and look at the math operations and look at your hardware. So you're using GPU. In GPU, we have levels of memory hierarchy and levels of and the threads, like CUDA threads, and also the tensor cores. So all of these resources are available, but how to use them best for your specific model. Let's say we look into the kernels, we go down into the math and see how we can increase the computation, so increase your occupancy to your GPU by keeping the memory access as low as we can. So the memory is the bottleneck, like global memory at GPUs is the bottleneck here. We try to bring up the occupancy, go hit the global memory rest, and kind of play Tetris with these mass operations to get this ML model running faster on the GPU. And at the end, we have a model scheduler, because our target are edge devices. And edge devices, when you can ask or like install, like for example, PyTorch on a robotic autonomous vehicle, for example, or a humanoid robot that goes and function in the world. They have something called like safety certifications. So that's why they need to know all the code that goes to the robot to do safety certification. We don't do safety certification. What we generate those code for them. So what we give them is a binary, but the binary has a very simple C file for scheduling the kernels and also modifying the data, like optimizing the data paths between these layers and creating the model as a whole as a binary that can be deployed on any edge device. So to go in detail, our compiler, as I mentioned, has two important pieces. Like we have an optimization set that we try to optimize parameters of your model based on the target hardware that you're targeting and the size of the data that you have. Is it dynamic? If it's dynamic, what's the maximum size? What's the lowest size? And we kind of continue in the loop, and we keep the target hardware in the loop. So we use the profiling and the output of your target hardware in optimizing your model as well. And that's helps us get to a better and a faster model. And sometimes faster is not the demand. Like it's combining multiple models that can run real time at the same time. How we can run them in parallel. How can we divide the resource between them? So these are also the question for the compiler as well here. Awesome. And at the end, a compiler should be easy for engineers to integrate. We don't want to create another tool that everyone, like similar, let's say to PyTorch, that everyone needs to onboard, everyone needs to learn. It would be a simple add-on to your training framework. And what is better than I take you to the compiler and show you how you can use it. Awesome. Okay, so when you go to compile at yasp.ai, you would facing a page like this. So at the moment, we haven't released this page. Our grand opening will be end of Q2 this year. But you're going to face a page like this. And then let me log in with my credential. And you're going to directly go to the dashboard. At the dashboard, you're going to see how many credits you or your company has, how many have been used. And if I go to compilation, you're going to see like I've been compiling on RTX 6000 Pro, or if I go to the other page, I think I have some 5090s here in the list as well. Yeah, some 5090s. And you see some of them like work, some of them doesn't. It's the way you do compilation with any compiler. And token. The token here is a way for you to communicate with our API. So our backend runs on a server. So you need to send the intermediate representation that we discussed over the network, and we take it and we send it through our backend. Basically optimization and code generation. Our API is compiled at yasp.ai/API. That's our API URL. And you need this key, the token, to talk to the API as well. And we have an evaluation runner because we want to give you back a model that has the correct kernels. So we spend time on building a very robust evaluator system, we call it internally. Our evaluator system does three things. Compiles the model, runs the model, and profiles the model. When it runs the model, we wanted to make sure it's correct. Let's say we had convolution and ReLU layer, and we fused them into a new fused layer, but we want to make sure that layer that is written by the agentic system is correct. So we run it through an extensive search with different types of random input, and we check the output, and the tolerance will be returned back to the user that this was the tolerance, like we have our tolerance, and we pick the tolerance based on PyTorch tolerance at the moment, but we also return it back to the customer like this was the relative error, for example, was 10 to the -6. So you know what you're dealing with for this specific kernel. And that's at the kernel level. We do that at the model level as well, and even submodel. Remember, I told you sometimes like we break the model into pieces. We make sure the metrics of model pieces are the same as well, and the metrics of the whole model is the same, unless the user wants us to go and like break the model and change the model. Let's say the user wants us to quantize. So of course the metrics of the model will be different. The user will be providing us either the metrics, or we tell them like, this is the going from FP32 to int8. This is the accuracy drop that you're going to see here. Okay, and by
a quick Reza, we had a couple of questions piling up. So before we get to the next
sure,
the next milestone here, couple of things. So let's go to a few things here. This one from Vinamra. What framework do you use for graph optimization? Is this MLIR-based? And actually, I think I saw this question a couple of times.
Good question. Good question. So we looked into what other compilers are doing. We looked into what TorchCompile is doing, MLIR is doing, and we also looked into what TVM is doing. And what we want to do back in the next step at the mass level in the coding agent. We need to have way more parameters than we will have way more parameters than these compilers already have. So we needed to generate our own optimizer, and our optimizer not only looks at the input data, also looks at your target hardware as well, and see, like, let's say you're talking about a matmul operation. But your target hardware is NVIDIA Thor. At NVIDIA Thor, you have FP8 tensor cores. So we can now, this is an opportunity to leverage those, and we're going to see a huge speed up. Of course, you can go with a simple operation of matmul on CUDA cores and get the job done. It would be also like a fast operation, but to squeeze everything from the GPU, we needed to develop our own compiler, and we do not like a machine learning algorithm to tune those knobs, basically, to get our, like, what should be the, like, let's say all the parameters, what should be the size, what should be the data type based on the target hardware. And that's why we had to develop our own optimizer and partitioner for this problem. Yeah.
Sounds good. My camera seems to be frozen up. Can you guys hear me okay?
Yeah, we do.
Can hear you well.
My camera's frozen. No big deal. So let's see. The other question was another one here from Emola. Oh, Emola, nice to see you. Is the compiler agnostic to the operating system of the hardware, of the target hardware?
Another good question. So the hardware agnostic is something that we are going for, but deep down, it's hardware aware. So right now, our agent can write Triton code, CUDA code, and HIP code, and this is how we get the hardware agnostic. So we enable our agent to write code for your target hardware. Let's say we're talking about Qualcomm. Let's say Qualcomm, we want to bring Qualcomm chips into our compiler. We need to generate, like, we need to kind of fine tune our agent to be able to write low-level code for Qualcomm chips. And how we do that is also very interesting. Like, first, we try to add knowledge base to our agent and use the model that we have currently to get the job done. But usually that's not enough, and we start reinforcement learning system with a data provided usually by the hardware manufacturer to start changing the weights of the model to be able to write code better for that target hardware. And you usually get to fast kernel because it's like a exploring the options to get, like, basically search for the best kernel. It can go forever. And if you have a good model that is we use reinforcement learning to fine tune it, then it can get to the best answer faster. Yeah,
I see. Okay. Dimitri, you want to pick one?
Yeah, sure. So the next question is from Deep Tech Stuff on YouTube. What kind of LLMs do you use for code generator? I did notice that you had that LLM code generation in your slides. What ML models are capable of understanding GPU hierarchy and generate code optimized for the memory hierarchy in a deterministic way? I think the last point is very important.
Question.
Yeah, that's a very good question. So I'll it's part of a multiple questions, so I'll tackle it one by one.
Sure.
So apart the LLMs, we're using open source and closed source models, but we have started seeing better results in our own, as I discussed, the reinforcement learning process that we have. We're getting best results from them, and we're working on them. So for now, all the 3 agents that I mentioned, not all of them are using our own model, and our own model is not baked that, but the focus is to use our own model because we are building something that can write fast code for like GPUs or any AI or ML accelerator. The second part of the question, the models, and so the question is, well, let me repeat the question. What ML models are capable of understanding GPU hierarchy and generate code optimized for the memory hierarchy in a deterministic way? That's a good question. So we find out that by engineering the context based on the profiling update, you can get these models to get you similar kernel. Of course, they are random. It's not going to be the same kernel every time. And the way we also do it, like, let's say you have a problem of running ReLU plus convolution plus ReLU plus add, let's say just hypothetically, on an NVIDIA Orin with the same, like the data size of your image is 720 by 720. So for this option, when we generate a kernel that we are happy with, we'll keep caching in your system that kernel. So next time, it has 2 benefits. Next time that you're running the agentic system, it will use that cached kernel as an input. So it's either going to generate a better kernel than that one or similar. If it's similar, we're going to keep the one that we have in cache. If it's going to generate a better one, then the better one would replace the cache. But it would get to a better one faster because it already starts from a good example. So we call it like internally we have like a offline search to put these kind of kernels into our database system, but also on the user side we keep a cached system as well to make sure the model. But how to teach the model to use memory hierarchy, that would also a lot depends on reinforcement learning and adding the knowledge base to the model.
Cool. Hey, why don't we let you get back to your demo for a sec, and then you can let's see here. We'll get you back over here. Ding, ding, ding. So, there you go. Okay, we'll hang back for a little bit.
Yeah, for sure. So we created this Jupyter notebook to serve as an example of how potential user of yasp.compile would use yasp.compile, and we try to show you like how we try to keep it the minimum of using like a change of code in your code base to use this compiler. So at first I'm just building like a model bringing a model from the model directory, and let me actually open this and go to the one that I'm going to run for you. So this is DeepSeek MLA kernel, so the multi-layered attention kernel part of DeepSeek, and you bring this, let's say you copy paste it from open source, or you have already baked your own model that you're happy with. The requirement for us is to have these model function here and to have the inputs and init inputs. So init inputs is required if the model is asking for something. Let's say you're freezing some, like you're inputting some shape when you're instantiating your model, and the get inputs, so as it says, it's the inputs of the model. And in this case, we're generating the batch size sequence, like a tensor of this batch size, sequence length, and model, like the dimensions randomly. So we use random data as input because I just want to show you like how the system performs. Going back to the Jupyter notebook and start running it one by one as well. So here I'm going to set the seed because I'm going to compare three things for you. Vanilla PyTorch, let's say original PyTorch, we call it reference PyTorch, and Torch compile and our compiler. And awesome, we copy everything to the device as well, and we check the device here. The device is an RTX Pro. It's a Blackwell chip. It's the latest architecture from NVIDIA. And two things that you need to set as your environment available is the API host and API token. So token is, of course, you have to do it because it changes for every person and every company. But the API host, there's a default one, and the default is compile.yasp.ai/API. And if we don't create a specific API URL for you, then it's the default one. Let's check to see the client is initialized, and then we load the model that we just imported by calling the model function and get init inputs to bring the model argument for instantiating the model and copying the model to device, in this case, a CUDA device. And next step is to submit it. So what you see here is a call torch compile on model reference. That's how torch compile works, and it returned back a model. We call it model inductor because we were using inductor as the backend of a torch compiler, and I think that's what's set by default as well. But how would you basically do the same line at YASP is you start a model, you start a compilation, sorry. You add the reference model, similar here, but we need more because we wanted to compile a model for your input data and your target hardware. We need to know what the input is. We need to know what the device is and configuration. So at the moment, if we go back at top, I left configuration kind of, I didn't add anything to the configuration except the target hardware that is selected by the system automatically. But we can add a lot here. Let's say the customer wants to say, like the user of this, they want to say no kernel fusion or no quantization. So all of these can be set here. But we leave it empty, and empty means the maximum optimization possible. So awesome. Yeah, the job submit. And when the job submits, you get an ID like this. And after that, we will, there are different kind of functions. This one will wait in the code, basically pause the code until the compilation job from the server is done. And when we can always check back with the with the system. So we designed it this way. When you put like a very large compilation job, you can go and do the rest of the work and then come back and see when the compilation is over. Sometimes our clients, I saw that like they're starting hosting the inference until like they get the optimized model and then replace the binary with the optimized binary on the fly. But usually for edge customers, they want to use this function because they want to wait until they get the final optimized binary. Awesome. And after that, how do you download the model? So you call this the client.result and add, of course, the compilation ID, what was the reference, and what was the input, and what was the device. You might ask, why do we ask for the inputs again? Because this is the input that we're going to test. Remember, I talked about the evaluator. We test every single piece of the model to make sure the kernels, the subgraphs, the graph itself, to make sure we're returning you the correct model. And when the output is the fastest is yasp compile and we return you the yasp compile, it means we're 100% sure this model is correct. And you see, like this is like an evaluator function that we have here, and it is, I think it's sitting here, yes. So you can see the code as well, but we expect the user will also have their own system to compare one model with another. If they don't, they can use ours for sure, but it can also be like checked by a user. So this, what it does, it basically upload the model to the GPU, try to run it to warm up the GPU, because what do I mean by warming up GPU is you want to make sure your kernels are in cache, because you don't want to measure the time of the kernel being loaded to the cache. And then after set a time, we're going to run it for, I think at the moment our set is 2,500 times. And after that, we receive a bunch of data for every single input, we run it that many times. And for a series of input, now we have gathered a lot of data. We create a distribution, find the median, and the median is the kind of the time we consider that kernel takes. And we also started reporting the standard deviation to see like how different, how scattered these numbers are from each other. Yep. And in this specific example for DeepSeek multi-layered attention layer, you see that we were able to, for inference job, 9.7 times, and compared to reference PyTorch and 9.5 compared to TorchCompile, accelerate the board. Okay, I think it's a good time, Pete, for some questions. Yeah.
Pete, I think
I'm on mute.
Yeah,
I can try to fix that. No problem. Yeah, we got some good questions here. Let's see. Here's one that we have for follow-up regarding the selection. Says, optimizer you mentioned is an extended dialect based on existing framework, or did you go around creating from the LLVM level?
Good question. So LLVM is like this, the system LLVM has, it's a search-based system. So for code generator, they already have the kernels generated. It's just a matter of, let's say, do I have a kernel for FP8 on fusing convolution plus ReLU on Jetson Orin or not? And if they do, they pick it. If not, then they would stay with convolution as a separate layer, ReLU as a separate layer. What we do, we find a candidate to be fused together, and we send it to our code generator, which is a live LLM agent code generator, to generate the code. And we get the model back, and we compare it with the available kernels. And if we are faster and also accurate, let's say 10 layers we fused into one, and we run those 10 layers in PyTorch, we gather data, we run those 10 layer like as one kernel on our side, we compare the output together. If we are accurate and we are faster, then we pick that kernel as the successful kernel here. Yeah.
Cool.
Nice.
All right.
Yeah.
Dimitri, you want to pick one?
Sure, absolutely. Actually, I want to pick two questions, and it's a very practical one. People are definitely interested in the platform. So, okay, first question is, what kind of edge devices supported so far? And kind of to follow up on it, there was another one. How can a user add new hardware, a custom accelerator, which is not yet supported? Yeah.
New targets.
Kind of related. Yeah, new targets and which targets are supported.
I think those questions are very good questions. So because of our customer base, we started with NVIDIA, Jetson, and then we also started adding Thor to our portfolio. But in general, it should work on any NVIDIA chip, but these are the two that we are heavily testing. On the AMD side, we have tested EPYC CPUs and AMD RTX lines of GPUs. For the embedded, we want to get into Ryzen AI, but Ryzen AI is with NPUs. So right now on our to-do list, NPUs is the first thing to be added. And going back to your next question, that was like, how can we add more kind of hardware support to this? It has to be true at the moment, at least the way that we design it has to be through us. And we are trying to like create a pipeline how to add a new hardware support. The reason it has to be through us at the moment is we wanted to make sure it's done right, and the agent that can write for target X in language Y, it does the good job. But we're trying to make this like an automated system as well. So in future, we don't have to go and onboard new hardware devices. But the hardware devices that we're onboarding are TPUs, NPUs. At the moment are like our highest priorities, apart from, of course, NVIDIA and AMD. Yeah.
Got it. So no Qualcomm yet?
We would love to
awkward.
No, it's okay. I mean, I'm sure there will be in future. So Qualcomm logo already somewhere. in the
Yeah.
presentation.
Exactly. I got it. Yeah. And I guess another question is, so how long does it take you to create new targets? I mean, I guess one of the challenges is, makes sense, start with NVIDIA because that is sort of like the de facto development platform, but there's so many new things out there. You know, there's the Ethos core from ARM that we're seeing pop up. There's, you know, what Qualcomm's doing, NXP's doing stuff, their own NPUs. We're seeing, you know, DeepX, you know, Furiosa, Rebellions. I mean, I can go on.
Yep.
How do you think about, like, I mean, is this a weeks, months? Like, how long does it take to kind of get something fully authenticated as a good target?
So to bring a new target, because the first time we built this compiler, we were mainly focused on SIMDs. And when you talk about NPUs have, let's say, the processor, and the processor have its memory, and the memories are of different processor connected through a DMA. So we need to change the way agent writes code for that target hardware. So I would give it like between like 1 month to 1 quarter for us to bring up a new platform, let's say NPU style accelerators. After we have NPU style accelerators, which we will have soon, adding NXPs or other, like even Ryzen AI, I think uses an NPU. So all those type of accelerators that uses NPU would be way, way faster. Yeah.
Cool. I had one here. Someone just mentioned about kind of which part of the code is open source, which part is YASP's work. I don't know if that's something you can speak to or need to go back to the screen on.
No, that's a good question. So at the moment, we were trying to build something and test it heavily internally. The thing is, with open source, we like open source, we support open source. But the issue with open source is we need to put resources on maintaining the open source product as well.
Right.
We wanted to actually open source some pieces of the compiler this quarter, but because of that, like, kind of human resource is the main issue here. With the launch of our product by July, you're going to see a lot of pieces of this compiler is going to be open source, as it's going to be needed. Even like when the thing is, like, we want to show you like everything. We want to open like how we create this intermediate representation, how we send the intermediate representation over, so all the customers kind of trust us that the data stays safe. And so all those pieces, our front end system, IR system, all of these are going to be open source. Of course, like, we have to see the timeline and how it goes. And the main limitation factor, to be honest, is the human resource.
Yeah, as always.
Yeah.
Yeah, cool. Okay, so let's see. We also have a few other things going on here. Do you have more demos to show, or are we just in question?
Yeah, so I wanted to show something. We're talking about switching to different hardware. I wanted to show this, how easy that can be done. So this is my terminal, and kind of the same code that you see. I forgot to delete the token, so don't use a token. You see it. It's not going to work. It's tied to my account for now. But the same thing, the same code, the same argument. But you see, like, the selecting the model here is empty. That, like, I can easily bring any code. Okay, let me do. This is line 23, and let me actually start with RegNet. So I'm pasting like the RegNet code from open source. Just the only thing that we added are the two functions that I showed you on the previous model as well. So purposefully here, I'm running a different model. And target, we already tried NVIDIA. Let me go and change it to AMD RX 9070. And save changes. And on the right-hand side, I'm running. So this script that I have because I'm on my MacBook, as you can see, this script basically copies the whole code base to the server, compiles it, and run it, and bring back the results. And the command in the quotation is the one that that's being run on the server. Hopefully the gods of live demo is with me today. And what happens now is the same thing. It goes over the model, create an intermediate representation, passes that intermediate representation. This model should compile very much faster than the DeepSeek one because this is way smaller. Sends the intermediate representation to the server. So it goes to the optimizer, goes to the backend code generator. All the kernels that are generated would be evaluated to make sure they get the correctness check, and then return back, fuse together. The whole model will be evaluated to make sure the model is also producing same metrics as and then we run this. So the whole change would be here to change the compilation target, and here for selecting the model, just to put your PyTorch model, and give us these two functions, that how to get the input, if you want to use real input or random input, or how to get the initialized input for the model. Yep. And yeah, something about the compilation time. Like so far, we have spent a lot of time building the compiler. The compilation time is taking a little bit longer. We have a lot of solutions that we can expedite the compilation time. So the compilation time, don't take it at days, as you can see it on the right-hand side. It will be way, way faster soon. And one of the fast ways is, instead of like having iterations of the model to get to the best kernel, we're trying to train the model. By train, I mean more fine-tuning than pre-training. Train the model to give us the best kernel that we, let's say, on the 50th iteration or 60th iteration at the first or second iteration. So that is, but the process of fine-tuning, whoever has done that, it's a tedious process, it's a hard process, but when we get those models, we're gonna see a speed up here in the in our compilation as well. Okay, so the god of live demos are not with me today. Let me just try it another time. And you can see if I wanted to show you these numbers because the numbers are on AMD are way more interesting here, because kind of like on CUDA devices, a lot of engineers have already optimize the models, but on AMD devices, it's there's still some work to do and to use like ROCm and HIP kernels to optimize. And you're going to see the power of these this compiler here, that it can optimize the model way faster. But something is wrong with our server at the moment. Okay. Let's we can take some questions until let's see like if the server is back and can help here. Yeah.
No problem. Yeah, it's always a little dicey doing the live demos here. Yeah. So
I'm happy the first one went well.
Yeah. I do have sound effects though, so I can do this. That's good. That helps lighten the mood a little bit. Yeah. Okay, so let's find some more questions. We got a few. Let's see. How about this one? This is a good one from Cedric. When evaluating inference performance, comparing yasp.compile versus reference, do you host the GPU at some server? How do you plan to host edge devices? We mentioned this sort of before, like a DSP or an NPU.
That's an amazing question. So we had this problem, like we're not going to have all the edge devices the customer has. We're not going to have all the GPUs that the customer has. And it's going to be a bottleneck here. What we decided is the evaluator tool that I discussed, the evaluator tool, we made it a separate tool that when you install yasp.compile as a pip package in your machine, it will install that evaluator as well. And if we do have a copy of your GPU, let's say you're running on H100, we do have access to one H100, we will profile it on our machine. But on edge devices, we never can claim that we have all the edge devices. We will run that binary, which is our evaluator, on your system. So the kernels that are generated is being sent back to your system, run on the target hardware that you're on, and then send back. It will send the feedback back to us, so we use it for kernel search. That's how we call it internally. Bring your own GPU. That allow us to expand the support of a number of GPUs that we have.
Okay, BYOG.
Yeah, exactly.
Cool. Let's see, Dimitri, do you want to pick one? We have a few starters.
Yeah, I actually had a question myself.
Sure.
Yeah. So first of all, like in concrete terms, what is the output? So after all optimization evaluation, what do you get? What sort of binary do you get? So
That's a very good question.
Hmm.
That's a very good question. So you have different choices. The first one, when you just run it as a PyTorch system, because your PyTorch model is an NN module, will return you back another NN module. And when we return an NN module, you can still use your weights, because we are not copying your weights to our server. Your weights stay on your side. You can still use your, like, it would be not useful if you had to retrain the model. So you can still use your weights as an NN module. But we know, as I mentioned, our edge customers, they cannot run PyTorch on their robots or embedded chips. The next step is the tools that we have, yasp.inference and yasp.edge. And what these two tools does, now we have a list of kernels, and we create you a C file. That C file's job is to, I should say C/C++. Its job is to create one file that contains all the kernel scheduling and kernel and data flow of your model. And then we have all the kernels separated in another directory. So your whole model will be probably like multiple, like 50, 60 files, and that can be compiled into one binary, and we'll give you a header file to access that. So we found out that a lot of, like, let's say robotic companies, they get the data from the cameras, and they want to pipe it to the model and connect the output to their motion planner or whatever else is coming after that. So having a clear API to send the binary image to the model and get the classification out would be crucial for them. Also, having access to the code, because what we're building is the compiler. The code that's out of the compiler is yours. Having the source code of that, a lot of edge customers can sleep better, because they know what are the dependencies, what library they're dependent, is this library safe to use in this environment or not. Yeah.
Awesome.
Nice.
Hey, by the way, I was going to show the for people that want to go to the YASP website and learn more. There's a QR code, so you can go do that. But we do have more questions. So let's see. More questions are coming in. So let's see. We got, well, here's one just about sort of performance. Can the compiler provide inference speed or memory usage gains over manual tuning? Like, kind of give you a before and after kind of.
Yeah. Yeah. And that's the goal. That's the goal, to decrease the memory usage and by sacrificing the computation. So you use more of the processors, at least on the SIMD products like AMD and NVIDIA GPUs. And yeah, that's the main goal.
Excellent.
Yeah. If we bring back the screen, Pete, I remembered, like, I ran this once before our demo. I don't know, like, it worked half an hour ago, but it doesn't work. It's not working right now. But these were the expected results that you can see.
Oh, there you go.
So to the question, this 5x improvement, for example, here that we get is exactly that. Just improving the model to use more process than memory. And this is the AMD 9070, RX 9070. and these are the inference and training. And like we're working on training as well, but although our main focus, because of our a lot of our customers are edge customers, and our main focus is inference, we do also look at training as well. And the difference, of course, everyone knows that like you need to keep track of the data and also generate backward pass kernel. So in general, it's a harder problem, but we're trying to keep ourselves a compiler for both training and inference.
Mm-hmm. Cool.
Yeah.
Let's see, Dimitri, do you have more questions you want to pick?
Yeah, absolutely. So there are some really practical questions, like the one from Yashwant Dagar. How does the billing work? Does user bring in their own GPT cloud keys and pay extra for YASP or project-wise, or native YASP key and pay directly to YASP? How does the cost compare to API keys of Cursor or GPT-5?
That's
exactly the money question.
That's a very good question. So no, because we don't know which model we're going to generate your kernel with, because like it's a multi-agent system. We even like we don't know if it's the successful kernel here would be the Triton kernel or the HIP kernel, for example, let's say in AMD case. And we don't know which model. Is it our own model? Is it an open source model that we are hosting, or is it one of the API calls that we have? So that for that reason, we will bear the cost of API call to the LLMs. That being said, we do have some customers that they want the whole system to be in their pipeline because of like how secure they want the data to be. That is also possible. So we can only work on open source model. It might take longer to get to a better kernel, but that's also doable.
Okay, cool. Well, let's see. Here's another one. What kind of profiler do you use, and is it dependent on every new hardware target? How does the agent summarize the profile information? This is from Shubham Rai.
That's a very good question. So profiling, like when we started building this, we knew that profiling is the most important. And if you look at the market of open source and non-open source, there are companies who are just building profilers. And there are open source project from PyTorch. Actually, I get to know that project when I was at the PyTorch conference this October. They were I think the name is kernel. I don't want to butcher the names. Like PyTorch itself is building a library to use PyTorch for checking the profiling of these, but we want to go to vendor profile. Like we want to use NSYS from NVIDIA or ROCm Info from AMD to get every nitty-gritty details of what happened with this kernel, like why this kernel is taking this much. And everyone in the GPU domain, they know you cannot trust the millisecond that the kernel run, because some kernels are so fast that it's very hard to measure the time. So we need to look at like how, like with the increased number of batch or different input size, how this kernel is performing, and not only look at the milliseconds, also looking at like how much of the cores it was engaged, how much memory, what was the page flop between the memory and the thread. Like all this information is being used to create a feedback to the model. Yeah,
got it. Hey, we're about to run out of time, so I appreciate that. The recording is on our YouTube channel for all time, all in perpetuity. So if you want to revisit it and share it with your friends, that's cool. I got the URL there to the YASP website. I'll give you a little applause sound effect here. There you go. Excellent. Yeah, no, it's been great having you. Thank you again, Reza. And I think hopefully everyone's learned a little bit about what's happening in the compiler space. Fascinating application of how AI is kind of affecting that, and absolutely necessary. So, Dimitri, thanks for co-hosting. Appreciate it very much. And hopefully we'll see some of you folks down in San Diego.
Yeah, for sure. And yeah, thank you for hosting me. It's been a pleasure, and hope to see everyone in San Diego. Yeah.
Sounds good. All right, everybody. Take care.
Take care. Bye.